This is the video recording of solving the questions for the grade 12 ASP end of year chemistry exam. First, when you get your exam, the first thing you're going to look at is the formula sheet that you have in your exam. Now these formulas, I will explain the formulas as I'm solving the worksheet. So let's first begin with the first question, topic 5.1, define radioactivity. So radioactivity is the emission of subatomic particles or high energy electromagnetic radiations by the nuclei of certain atoms. Such atoms are said to be radioactive. So I can say radioactivity refers to the process by which unstable atomic nuclei lose energy by emitting radiation. So usually we have an unstable nuclei that has a lot of energy and it's going to emit radiation and radioactive particles. The second question, list the common particles and their symbols used in description of radioactive decay and nuclear transformations. Now this question is really important as you are going to use these radioactive particles in almost every single nuclear reactions. So let's begin. We have the protons. We have the proton. The symbol of the proton is P+, and the nuclear symbol is either a hydrogen with 1 as a mass number and 1 as atomic number, or you can simply write it as P proton 1 and 1. Another particle is the neutron. The symbol of neutron is N0, and we say 0 because it has no charge. Proton I put plus because it has a positive charge. Now the nuclear symbol of a neutron is N10. Now electron, or you can say beta, I'm going to make them separate because electron, I use it in the electron capture, and the beta, it is usually obtained in emissions as beta decay. Okay, but these are almost the same particle. So the electron, the symbol of electron is E minus, and for beta, the symbol could be beta symbol, or you can say beta minus. Now the nuclear symbol of the electron capture is E0 minus 1, and as well for the beta. And for the beta, instead of writing E, you can also write beta 0 minus 1. Other than the proton, neutron, electron, or beta, we have the alpha particle. And the alpha particle, the symbol is alpha, or the nuclear symbol is it's an atom of helium 4 2, or you can simply write alpha 4 and 2. And there's one more, the positron, which is different than the proton. The positron is the beta positive. And the nuclear symbol of this one, you can say beta 0 plus 1. So it's different than this one. It's plus 1, the positron. Or you can simply put E, and instead of 0 minus 1, you're going to say plus 1. So basically, these symbols, you really need to know them very well before your exam. Now, another question asking to describe gamma rays. Gamma rays, that's gamma, it's a gamma radiation, and it consists of high energy photon It's an electromagnetic radiation of a very short wavelength. So I'm gonna write this one over here. It's a high energy photon particle. It's a type of energy. So it's a high energy photon particle, and it consists, it's electromagnetic. It's an electromagnetic type of radiation. How gamma rays are represented, the symbol or the nuclear symbol of gamma rays is gamma 0 and 0. So 0 atomic mass and 0 atomic number. Now, moving on. Complete the table. Nuclear equation showing a positron emission. What's going to happen in the atomic number and in the change of mass? I'm going to give you an example just to make this clear. Let's say, for example, I have oxygen 15 as a mass number and 8 atomic number, and it's going to emit a positron. It's going to emit a positron. So it's E 0 plus 1. Now the atom obtained is gonna have the same mass number because 15 plus 0 will remain as 15. So the mass number will not change. Now for the atomic number, because here there's a plus 1, so we need to decrease the atomic number by 1 and put it as 7. So like this, 7 plus 1 gives 8. So this is the nitrogen symbol. So the atomic number, it's gonna decrease by 1. So this is how I can explain it as an example. Now let's take the electron capture. What could be a good example for electron capture? So let's say we have potassium, okay? So let's say we have potassium 4019 and it captures an electron. What's gonna happen to the new atom in terms of atomic number and mass number? The mass number is gonna stay the same because 40 plus 0 is 0, but the atomic number is going to be 19 minus 1, that is 18. Now 18 is argon. So again, the atomic number is gonna decrease by 1, whereas the mass number will not change. It's not gonna change. Let's move to the next multiple choice question. Which of the following correctly describes alpha decay? As I said, it's a helium atom, or I can represent it by alpha and 2. So it's a nucleus. A nucleus emits an electron. That's wrong. A neutron transforms into a proton and emits beta particle. That's wrong. It's a helium nucleus. That's correct. And it's emitted usually from an unstable nucleus. Now describe the positron particle. As I mentioned, the positron is beta plus, or E0 plus 1. So I'm gonna write the symbol. Okay, so this is the representation of positron particle, and it has the same mass of an electron. You see, this is the positron, and the electron is simply the same but minus 1 instead of plus 1. So we use the same letters. It has the same mass of an electron, but the charge is positive. So that's why I call it a positron. It's a positive particle. Moving on to the next question, and in the nuclear equations, when they ask you to write a nuclear equation, this is where you need to use the periodic table. So first of all, it says thallium, write a nuclear equation for the formation of thallium from uranium. So I have uranium and giving me thallium, it's TH. If you don't know the formula, you can go and look for it in the periodic table. Now always when they give you the name, they give you the mass number and not the atomic number. Why? Because the atomic number, I can get it from the name. So this one is gonna be here 234, and for the uranium it's 238. Now let's go to the periodic table. In the periodic table, that is the uranium over here. So the atomic number is 92 and the thallium is 90, TH90. So here I'm gonna write 90 and here I'm gonna write 92. Now in order to balance these equations, the mass number, they should be equal, and the atomic number, they should be equal. Now since I have here 92, I'm missing here 2. So 90 plus 2 gives 92. And this is 238. Here I have 234, so I'm missing 4 as a mass number. Therefore, the particle emitted is an alpha particle, a helium atom. Write a nuclear equation for the isotope carbon 11 decays by positron emission. So I have the carbon, which has a mass number of 11. Now I'm gonna go to the periodic table and get the atomic number of carbon, and that is 6. I'm gonna go and show it to you, and it's gonna decay, it's gonna change into another atom, another nucleus, and there is positron emission. As I said, the positron is E0 plus 1. Now let's see what's gonna happen. This is 11 and here is 0. It means again I still have 11. Now this is 6. It's gonna be 5 plus 1 to remain as 6. Now let's go to the periodic table, and here's the carbon. As I told you, the atomic number of carbon is 6. Now which atom has atomic number as 5? It is boron. So the new symbol obtained is the atom boron. Write a nuclear equation for the conservation of a neutron to a proton. So I have a neutron, and again here's the symbol of neutron, and it is converted to a proton. So here's the proton. You can say H or you can say P. It's okay. So it's basically the same. So here's a neutron. The nuclear symbol of neutron is N1 mass number and 0 atomic number, and it's converted into a proton. So it's 1 and 1. Now since the mass number is 1, so I'm gonna get here a particle with a 0 mass number. Now this is 1 and this is 0, so definitely I have a -1 because 1 minus 1 is a 0. So which particle is this? This is beta, or you can write it as electron. Now in some other questions, they're gonna give you the equation and you're gonna find out the missing product. So I have phosphorus, this is 32, it changed into sulfur, it's still 32. So I have here a particle with 0 mass number. Now 15 turned to 16. Now in order to keep it 15, I'm gonna put -1 because 16 minus 1 is 15, and that is electron, or you can say beta decay, electron emission or beta decay. Radon 222 undergoes alpha decay what's the resulting nuclide? So radon, let's go to the periodic table. And here is radon. It is 86. This is radon, and it's gonna undergo an alpha decay, Rn 86. So I'm gonna write here Rn 222 as a mass number and 86. It's gonna undergo an alpha decay. That's 4 and that is 2. So what's the mass number remaining? 222, and here there is 4, so it's gonna be 218, because 218 plus 4 is 222. And since I have here 86, then here definitely it's gonna be 84. Now looking at the options, that's the correct answer. And if you check in the periodic table, you're gonna find polonium with 84 atomic number. Explain how a nuclear equation represents mass number and atomic number conservation. So as you can see in the previous questions, I am making sure that the mass number on both sides, reactant and product, are equal, and the atomic number are equal. So a nuclear equation must be balanced in terms of mass number on both sides, A, and atomic numbers on both sides, which is the one written to the left side below. Symbol is Z. So it's like this, A and Z. Name the main types of radioactive decay. So I either have alpha decay, it means we obtain alpha as a product, or I have a beta decay. So here's the alpha decay, here's the beta decay, or gamma radiation. Now, I was going to mention electron capture, but in the question, they mentioned the decay. So electron capture, it's plus electron. So it's added to the parent nuclide. So it's not a decay. So the main type of radioactive decays are these 3 types of particles. What particle is produced during the following decay process? I have actinium 215 decays into francium 211. Now actinium in the periodic table is AC 215, and it's going into francium 211. Now let's go to the periodic table to get the atomic number of actinium. Here's actinium. This is the one, 89, and the francium is Fr 87. So 89 and 87. So actinium is 89, francium is 87. If you look at the differences here, 87, and here we need to take it to 89, so there's a missing 2 as atomic number, and 211, taking it to 115, that's 4. So, which particle is produced during the following decay? Alpha particle is produced. What do these symbols below stand for? That is gamma ray, that is alpha particle, and this one, this symbol, part C, that's a neutron. Now, let's write now the difference between isotopes and nuclides. So isotopes usually are atoms of the same element, but these atoms have different number of neutrons, therefore their mass number is different. So I'm gonna give you an example. So let's say we have, let's take the example of uranium. Okay, so I'm explaining the isotopes. So I have uranium 235 and I have another isotope of uranium 238. Now why these are isotopes? Because both of them, they have the same symbol, uranium. Both of them, they have the same atomic number. But what's the difference between them? The difference is in the mass number. So they have a different mass number. And what's the reason? Why do they have a different mass number? Because they have different amount of neutrons. So if I subtract 235 minus 92, the first one has 143 neutron, whereas this one, 238 minus 92, 146 neutron. And that's why I call them isotopes, because they are elements, atoms of the same element having the same atomic number, and because they are the same element, so they're gonna have the same symbol. But the most important thing, they have different number of neutrons, resulting in a different mass number. Now the nuclide, what is a nuclide? It's the nucleus of the isotope. So it is the nucleus of an isotope. And not all the atoms of the periodic table are radioactive. Majority are non-radioactive. I mean the opposite. So less than 10% of the nuclides are non-radioactive and majority are radioactive. So how do I represent a nuclide? A nuclide is represented by the symbol, and on top we have the mass number, and below we have the atomic number. So A is the mass number and Z is the atomic number. Now if I want to find the number of neutrons, I simply subtract A minus Z. Compare chemical and nuclear processes. So what they're asking you here is to compare between a chemical reaction and a nuclear reaction. And these are two different things. So first of all, chemical reaction involves a certain amount of energy, but the nuclear processes involves a huge amount of energy. So chemical reaction, energy absorbed or released is a lot less than the energy absorbed or released in a nuclear process. That's one. Second, in the chemical reactions, atoms are conserved. It means bonds are broken for new ones to form, and I still have the same atoms. It's the change occurs in the electrons. The change occurs in the valence electrons outside the nucleus. Okay, so if I have Na plus Cl2, it's gonna give me 2NaCl, and here's the balancing. Na still there, Cl still there. So what happened is that Na and Cl2 exchanged electrons, and I have a chemical process. But in the nuclear reactions, it's completely different. The change, so in nuclear reactions, the change takes place inside the nucleus. The change takes place inside the nucleus, and not like in the chemical reaction. It's outside the nucleus. Here, inside is in the nucleus at the level of protons and neutrons. The atom is changed into a new one. The atom changes completely into a new one, and a huge amount of energy is released, and a huge amount of energy is released. So here we saw so many examples. The atom itself completely changed. So here I have actinium, and it changed into francium. It's a completely new element. So we have, it involves the formation of a new element. So new elements are formed. That's something very important. In the chemical process, I still have the same elements. Moving on to the next question. Which of the following statements about nuclear reactions is correct? They involve the transfer of electrons. That's chemical reaction. They produce less energy than chemical reactions. That is wrong. Actually, the chemical reactions produces less energy. They involve changes in the nucleus, and they can create new element. That's the answer. And definitely not at room temperature. The temperature usually in nuclear reactions is significantly high. It's extremely high. Now, the next question is to differentiate between fission and fusion. So, fission, I have a large nucleus that's usually unstable. It splits into smaller nuclei, and it results in the release of a large amount, a huge amount of energy and radioactive particles like gamma, beta, alpha, and these particles. Now, that's for the fission. So a large nucleus, it's gonna split into smaller one. Now in the nuclear fusion, it's the opposite. I have combination or combining smaller nuclei into a heavier one, heavier and larger nuclei. But again, it involves a large amount of energy. So I can give an example. Let's say I'm gonna give you here just a second, looking for the right example. So I'm gonna write it over here. So for the fusion, I have, for example, two hydrogen in the sun combining with deuterium, combining with tritium in the sun, and we get helium and a neutron. That's fusion, and a huge amount of energy is released. Now, for the fission, an example of fission could be uranium 200, let's say 35, the atomic number of uranium is going to be hit. Usually for the fusion to happen, we need to bombard the atom by a particle. So let's say we hit it with a neutron, and it's gonna turn into 236, which is unstable. So this atom is so unstable. So what happens, it's gonna undergo a fission, and in here it's gonna give me two smaller atoms, the krypton and the barium. So the krypton, so you don't have to memorize these equations. I'm just giving you an example so you can see the difference. So krypton atomic mass is 36 and barium is 56. It's over here. So 36 and 56. So I'm gonna write it 36 and 56. Now if I add 36 and 56, I'm gonna still get 92. So as you can see here, I obtained two smaller nuclei, where here I have two smaller nuclei giving me a heavier one. Let's continue. Which statement about nuclear fission is correct? It combines fission, it combines light nuclei, that's fusion. It occurs naturally in stars. Actually, the fusion occurs in stars. I'm gonna write that over here, and in the sun. It involves splitting, that's fission, heavy nucleus into smaller nuclei, releasing energy. So this is the correct answer. Identify the order of kinetics for nuclear reactions. All nuclear reactions follow the first order of kinetics. First order of kinetics. And in the formula sheet, the formulas are given to you, so I'm just gonna show it to you. First order kinetics. So if you go to your formula sheet, here are the formula that you need. This one you don't need, this one you don't need. So you're gonna need this one, that's first order, and this one is the t-half of first order. So basically these are the two formulas needed throughout your calculations. So the second and the fourth. Remember this information. Define half-life. What is half-life of a nuclear reaction? It's the time required for the amount of reactant to decrease to its half of its initial value. So the half-life is the time required for the amount or concentration or mass or whatever quantity of parent nucleide you have, the amount of reactant to decrease to half of its initial value. So the time taken will be will be called T half. So for example, if I have a sample of 20 gram, now for the sample to become 10 gram, half of its original amount, the time taken is T half. A radioactive isotope has a half-life of 3.80 days, 8 days. So T half is 3.8 days. If 0.57 grams remains, so that is A at time T, after 5.5 days, so that is T. What is the initial mass, which is A0? So again, as I said, we're gonna use the formula in your formula sheet, which is ln AT minus ln A0 equal minus KT. K is the rate constant, and the T half, there's another formula, T half is 0.693 over K. So first of all, we need to find K. I'm just gonna give you the given. 0.57 is this one. 5.5 days is T. T half is given over here, and it is this one. So the question is asking me to find, let's take another color, to find the initial mass, which is A0. So first of all, let's find K, or let me just substitute immediately. So ln 0.57 minus ln A0 equal minus KT. Now K is gonna be 0.693 over T half. So 0.693 over T half, which is 3.8 days. I don't need to convert because the time in this question is days, and T is 5.5 days. Now plugging this into your calculator, you're gonna find out that A0 is 1.55 grams. What is the half-life in the graph below? Expect in your exam to have graphs. So you first look at the initial amount and you divide it by 2. So 1 million, half of it is 500, which is this point, almost here. So the time taken for the 1 million to become 500,000 is 1 minute. So T half in this graph is 1 minute. Define radioactive dating. Radiometric dating is a technique used to determine the age of objects by analyzing isotopes and their abundance. So this is the radioactive dating is a method that usually geologists use to determine, is a method that helps determine the age of like materials like rocks, fossils, artifacts, etc. And it measures by measuring the decay of radioactive isotopes and comparing the amount of parent isotope to the one obtained. To daughter, we call it daughter isotope, product, of course using the half-lives. Now in the next question, they are asking you to list 2 types of radioactive dating. There are so many types. In your answer key here, you have the mineral, which is the geological dating, and you have the radiocarbon dating. Now I'm gonna list some and you can remember whichever you want. So the radiocarbon dating, usually it uses carbon. It uses carbon and the isotope carbon 14, specifically not carbon 12. So it uses carbon and it's used for bones, wood, to determine the life of bones. When we have like if they, the skeletons, so used for wood, bones, and it can measure like things found from 50,000 years. It's effective for up to 50,000 years. Okay, and it measures the remaining C14 compared to nitrogen 14. So as I said, here it compares the amount of parent isotope to daughter isotope. So in the radiocarbon dating, it measures the remaining C14 and compares it to the daughter compared to nitrogen 14. The daughter here will be nitrogen 14. So by this they can determine the age. There are other type of radioactive dating. You have the uranium, lead dating. So the parent is uranium and they compare it to lead, and it's usually used for very old rocks, millions to billions of years. You have the potassium argon dating. So the parent is potassium, comparing it to argon, potassium argon dating, and this one specifically for volcanic rocks. So I think that's enough. There are still more, but this is enough. The most important one is the radiocarbon dating. This is the most famous one. Now, let's move on with our topic, moving to topic 5.2. The 3 variables that influence the absorbance of a solution. So in this topic, you have to learn about the concentration affected by the absorbance. So we measure the absorbance in order to know how much is the concentration. And Beer-Lambert's law is usually used to find out the concentration of specifically colored solutions. So if I look at the formula, absorbance is molar absorptivity multiplied by the path length of the light multiplied by the concentration. So A is the absorbance. Now they asked me to list the three variables that influence the absorbance. This one is called molar absorptivity, and it's usually constant and specific for every solvent with a specific wavelength. Now B is usually the path length of light through the solution, the cell length. You know the cuvette that you use to put in the colorimeter, it has a path length. So this is the distance that the light travels. And this one is the concentration. Now concentration in molarity, path length usually in centimeter, which is correct. So let's see this sentence or this sentence. So absorbance is affected by the concentration of a solution. Of course, the higher the concentration, the more the absorbance. So this is correct. Absorbance is not affected. This is wrong. In Beer-Lambert's law expression, what does A stands for? A is the absorbance of the solution, absorbance of light by the solvent of the solution. Now, calculate the absorbance of a solution with a concentration of 0.015, molar absorptivity 200 liter per mole centimeter, and the path length of light is 1 centimeter. So absorbance is absorptivity times B times C. So it is 200 times 1 centimeter times 0.015. So this is going to be 3. Absorbance has no unit. Calculate the absorbance of a solution. Again, we need to calculate the absorbance of a solution with a concentration of 0.03, molar absorptivity 150, and the path length is 1 centimeter. So it's 0.30 times 150 times 1. And the answer is 4.3. Again, absorbance has no unit. Now, write Beer's law expression. This law, it's not given in your formula sheet. It's epsilon. This is the symbol. B multiplied by C. Now, let's look at this graph. Describe briefly the graph. We are looking at a graph showing the relationship between absorbance and concentration. From the graph, absorbance and concentration are directly proportional. Absorbance and concentration are directly proportional, and this is represented by a linear graph. Now, we can plot when we prepare a solution. Usually what we do, we prepare a solution, different solutions of known concentrations. Here they're calling them standard 1, 2, 3. So these are solutions of known concentration, and we measure their absorbance with a colorimeter. And after we measure their absorbance, we plot the graph. And then we are given a solution with unknown concentration. And we put this unknown concentration in the colorimeter, and it's going to give us a certain absorbance. So we plot this absorbance on the graph, and from the graph we can determine the concentration. Moving on to the questions of subtopic 5.3. Which type of orbital are most non-metals except hydrogen and helium fillings? If we look at the periodic table, we see that we have two elements block group 1 and group 2. Then we have the transition metals in the middle, and then we have, it looks like that, and then we have in the periodic table on this side some non-metals coming. So if we look at the blocks, if we name the blocks of these elements, here lies the element of the S block, D block, P block, and below here you have the F block. Now, if I want to answer this question, I need to know where non-metals are located. And the non-metals are located basically all over the side. And these are the elements of the P block. So that means their electrons are filling the P orbitals. The P orbitals. Except, now why they are telling me except hydrogen and helium? Hydrogen is a non-metal, but it's in the S block element, and helium also is a non-metal, and it has the configuration ends with 1s2. So hydrogen and helium are the S orbitals, or are filling the S orbitals, while all the others are filling the P orbitals. Why boron is considered a semi-metal? Boron is exactly over here in the periodic table, here in this box, and here starts the stairs of the periodic table where we have the metalloids. Okay, so boron is a metalloid. And what does that mean? Metalloids are the elements that have the properties of metals and of non-metals at the same time. So we call them, for example, why we call them semi-metal? Metals are good conductors, while non-metals are bad conductors. So when we talk about metalloids, they are in between. So we call them semi-conductors. Also, they are semi-metals. They have some properties of metals, but at the same time, they still look like non-metals. They share some of their properties. Next, explain how the location of non-metals on the periodic table affect their bonding properties. Okay, so let's first locate the non-metals. The non-metals are on the right side of the periodic table. They are on the right side of the periodic table. Okay, now how their location? They are non-metals, and non-metals means they gain electrons if they are involved in an ionic compound bonding, or they share electron. Okay, so either they gain, or sometimes, so here if they are in the ionic, and here if they are in the covalent bonding. So if the non-metals bonds, so if let me make it just clear, if they bond with other metals, so if they bond with metals, they will gain electrons and form ionic bonds. Ionic bonds. The question is asking me about the bonding, so I have to be specific. If they bond with other nonmetals on the periodic table, with other nonmetals, they will be sharing, they will share electrons and form covalent bonds. Okay, let's continue. Moving on, explain the chemistry of boron. And when they ask me explain the chemistry of boron, so it means mention where is it located, which period, is it a metal, is it a non-metal, some of the uses of boron. So boron is a group 13 element. So it belongs to group 13. Let me show it to you in the periodic table. Here, this is boron. It's a p block element. Okay, so it's element in the p block. So let's just group 13. It has, let's talk about the chemistry. It has a lot of allotropes, it means networks of boron, allotropes. And it is used in glass manufacturing. Remember this, manufacturing. Like for example, in the lab, we have beakers and glasswares. All of these glasswares are made from pyrex, and pyrex is the borosilicate glass. Is the borosilicate. It's the borosilicate glass, which contains boron. Okay, and also one of the important things about boron, it is used in control rods of nuclear reactors. So it expands كمان for the boron. It expands if it's heated. The glass expand when heated. So glass expand when heated. Now, the next question, to differentiate between graphite and diamond. Now, I need you to memorize this part in this table, the differences between them. Now, let's just look at the structure of graphite. You can see, for example, that every carbon has 3 bonds. Every carbon has 3 bonds. And usually carbon belongs to group 14, so it must have 1 bond. It means there is 1 free electron floating around. Whereas if I look at the diamond structure, every carbon is having 4 bonds. So there are no floating, no free electrons. So saying this, so here I'm just gonna say graphite has covalent bonds, and every carbon is bonded to 3 other carbons. Okay, so therefore 2 things result from this. It means the bonds are not so strong, so there are weak interactions. It forms layers, okay? So there are weak interactions between the layers of carbon, and this makes it a good lubricant. Another thing, the free electron, there is 1 free electron floating one free electron from every carbon floating between the layers, from every carbon floating between the layers, or you can call them the sheets, making the graphite a good conductor of electricity. Okay, so that's why graphite is a good conductor of electricity. Now, a graphite, if I look at it as well, these layers or these sheets, they have hexagonal shape, hexagonal shapes. So remember this, okay? And they can slide past each other, and the intermolecular forces exist in between. So these sheets, they slide past each other, making it a good lubricant, and the free electrons floating around make it a good conductor of electricity. It's not very strong. Now, what else other things we might know about this one? So graphite is soft, greasy feeling. It's, as I mentioned, conduct electricity. It reacts with acids and oxidizing agents. You have to know this because carbon has this property. So reacts with acids and oxidizing agents, and it's used, a graphite, whenever I say graphite, one should remember the pencil, okay? So as uses, it's the pencils, okay? So the lead, it's like, and if you touch the pencil, it feels like it is soft. It's a solid lubricant because it's mixed with lead. The graphite is mixed with lead, so it makes it a solid lubricant. Now, if I look at the structure of diamond, also in the structure of diamond, I have, as I mentioned, I have every carbon bonded to 4 other carbons. So it's kind of a tetrahedral shape in this network. Now, every carbon has 4 bonds. So every carbon is bonded to 4 other atoms. So there are no electrons floating around, and this is not a good conductor. It doesn't conduct electricity. However, diamond conducts heat, thermal conductor. Okay, so now let's just continue this idea. Every carbon is bonded to 4 other atoms of carbon, and as a result, this makes diamond very hard. And honestly, diamond is used usually as a cutting tool. So used as a cutting tool. Now, the next thing, as I mentioned, every carbon has 4 bonds around it, so it's making a tetrahedral shape. So the network has a tetrahedral network of carbon atoms bonded together. Other properties, it has a good, it's the best thermal conductor. It's used as a cutting tool. It's transparent. Just imagine the diamond and start describing it. It is transparent and it's very hard. It's the hardest and stiffest. It's not really compressible, least compressible. It is used in jewelry. And non-abrasive coatings. Cutting tool, cutting tools, and non-abrasive coatings. Expect a question probably about graphite and diamond given in form of a multiple choice, and you have to choose one of its properties. Which of the following is a form of carbon? As I mentioned, that carbon has so many allotropes. Allotropes. So, ozone is O3, that's not carbon. That's the allotrope of oxygen. Now, fullerenes and graphene are two forms of, are two allotropes for carbon, but that's not everything. So let me just put all the other options of carbon allotropes. You have the graphite. We just did the difference between a graphite and diamond. And we have the fullerenes. We also have, for example, the carbon nanotubes. So basically, these are the allotropes of carbon. So a question like this, which of the following is a form of carbon? Any of these choices would be a correct choice. Now, list forms of amorphous carbon. Amorphous carbon, it means when the solid carbon are solid, the particles of carbon are together next to each other, but they are not taking an ordered arrangement. They are arranged in a, like randomly. So unordered or random, not orderly arranged. And what that could be. Charcoal is an example. Coal, charcoal, or coal. The soot, you know, that black thing when it comes, when something is burning, you have like that black thing forming it. We call it soot, or carbon black, also known as carbon black. Coke. So I guess these are some examples that I can remember now. Moving on. Identify some general properties of nitrogen. And when they say general, it means just talk about nitrogen in general. So first of all, locate nitrogen in the periodic table. It is in group 15, period 2. Okay, now let's look at what's in the periodic table. It has 7 electrons, or you can say with an atomic number 7. Atomic number 7. Let's keep the properties general. So it's in group 15, the second period. Nitrogen exists or can form a diatomic molecule. You know that we have 7 diatomic molecules in the periodic table. We have N2, we have O2, we have H2, we have Cl2, F2, Br2, and I2. They are 7. So nitrogen is one of them. So we call it a diatomic molecule. Also, let's talk about the bonding. Nitrogen can form multiple bonds. And I mean by this single or double or triple when it bonds with other atoms. But N2 specifically, the bonding in N2 is a triple bond with one lone pair of electron on each atom. And also when they tell you general properties of nitrogen, let's mention the electron configuration of nitrogen. So I said it has 7 electrons, so 1s2, 2s2, and 2p3. So these are the basic, the general properties of nitrogen. If they want to talk about the uses of nitrogen or where do we find it, it's usually found in the atmosphere, on the Earth's atmosphere. Like the air has so much nitrogen in it. We have liquid nitrogen used to make things very cold. So just some general properties, whatever you can remember from nitrogen. Now let's move on to phosphorus. Some properties about phosphorus. Again, same thing. Phosphorus is located in group 15 of the periodic table, but this time it's period 3. It's in the third period. Okay? Now, one of the things that phosphorus, so let me just continue to do it the same as nitrogen. It has 15 electrons. It means the atomic number of phosphorus is 15. Now, it doesn't form a diatomic molecule, so I'm not gonna tell you I have P2. Yeah, I forgot. In nature, exists as gas at room temperature. Nitrogen exists as gas at room temperature. Now let me go back to phosphorus. Phosphorus can exist in different allotropes. We have P, we have P5, we have P8. We have a lot of allotropes for phosphorus. Do you really need to know them? No. So, it exists in the solid form. It has, I'm just gonna name them, like white phosphorus, red phosphorus, black phosphorus, violet phosphorus. This is how the allotropes of phosphorus are called. So it has white, red, black, violet, four allotropes of phosphorus, and each one has a different use. I don't need to know. I don't need to know them. It's solid at room temperature. And let's put the electron configuration just like what we did in the nitrogen. 1s2, 2s2, 2p6, 3s2, 3p3. You see here in nitrogen I end with 2s2, 2p3. Here I end with 3s2, 3p3. That's 3. It doesn't look like 3. Let's continue. Which element is extracted from the ground primarily in its elemental form? Like it exists naturally as element, naturally as an element in the on the earth. So we extracted as it is. Boron is existing as bonded to other atoms like boron oxide. Phosphorus as well. Fluorine, it does not exist as F2 like in the elemental form. We have to purify it. But sulfur, we can find it in mines underground. Fluorine, also another thing that's a gas, it's not underground. So sulfur is found on the ground, on earth, in its elemental form. List 2 chemical properties of sulfur. So let's look at the properties of sulfur. It's a non-metal. Let's list other properties. So sulfur is a non-metal, has allotropes, for example. Let's say it has an electron configuration ending electron configuration, just like oxygen, ending in S2P4. However, sulfur belongs to period 3, so we say 3S2, 3P4. It forms a -2 oxidation state, but it can have other oxidation states. That's not the only one. It is electronegative. It is electronegative, but not as much as oxygen. So that's these are some of the properties. It forms a negative ion. By simply saying it forms a -2 oxidation state, so it means in ionic compounds it has a -2 charge. Now let's move on with the questions. Describe the properties of elemental oxygen. When they say elemental oxygen, they mean oxygen as element in elements, and we have O2 and we have O3. So oxygen has allotrope, which is the oxygen exists in two allotropes as O2 and O3 allotropes. Let's discuss some properties. O2 is a diatomic molecule. Let's think about oxygen. O2 is gas at room temperature. O2 is so much available in the atmosphere. Available in the atmosphere. If I look at the periodic table, it belongs to group 16 and it is in the second period. And as a configuration, as I said, it's just like sulfur, but instead of being in the third period, it's in the second period. So the configuration will end in 2s2 and 2o4. It's a gas at room temperature. It's colorless, odorless, and we need it to breathe. Now, moving on, the next question, describe the properties of ozone. What is ozone? Ozone is the allotrope of oxygen, and it is O3. Where do we know, or where do we find ozone? It is found in the upper atmosphere. Let's just think about what do we know about ozone. Doesn't ozone protect us from the harmful UV light radiations coming from the sun? So it protects, or let me use another word. How does it protect? It reacts with those radiations and it prevents them from reaching the lower layer of the atmosphere. So it absorbs the UV radiations coming from the sun which are harmful. Oxygen is very important for life on Earth because it protects us from those UV light, because UV light can kill almost everything. It damages the tissues, it's not good for the plants, so it's very important, the ozone, to be in our upper atmosphere layer. Now, it has resonance structures. Resonance structure. What do I mean by resonance? Resonance means it's a correct Lewis structure. So if I draw ozone, oxygen, 3 oxygen atoms will have 1 double bond and 1 single bond, and the rest of oxygen will have, like the one here, will have 3 lone pairs, whereas this one will have 2 lone pairs, and this one, because it has the maximum number of bonds, like higher than the other 2 oxygens, it has 1 lone pair. That's a Lewis structure, option 1. And I can draw ozone as well like that, because the electrons, they can move between the atoms, and I will have the double bond on this side. Remember, the one with 1 bond will have the rest as lone pairs, so it will have 3 lone pairs. The one with 2 bonds or 1 double bond will have 2 lone pairs, and the one with 3 bonds, yani 1 single and 1 double, will have 1 lone pair. So these are resonance structures. So properties of ozone. So I talked about allotropes. Yeah, one more thing about ozone. Ozone, I'll write it in red, kills bacteria, and very important for the environment. Okay, so this is important to remember it. List some uses of ozone. What can be used? So ozone, some uses. So it's a good replacement, can replace chlorine. You know, in the pool we add chlorine to purify the water of the pool. Ozone can be used instead of chlorine, so can replace chlorine in water purification. That's purification. That's one use. Now other important uses, it kills the bacteria. I don't know if I can take this as a use. It oxidizes organic compounds. Oxidizes organic compounds. Ozone is widely used in pharmaceuticals, in medicines, used in pharmaceuticals, and synthetic lubricants. Explain how oxygen is extracted from the air. So I'm gonna clarify how oxygen is extracted from the air. I'm gonna write over here question 49. So first of all, air is a mixture of gases. Mainly it has nitrogen, it has oxygen, and it has other gases. So what happens to get pure oxygen? The scientists, they use a process called fractional distillation of liquid air. So what happens in order to get the oxygen? So first of all, the air is cooled. So step number 1, air is cooled to a very low temperature until it becomes liquid. So air is cooled to a very low temperature until it becomes a liquid. That's step one. So this is where we call it liquid air, or we liquefy the air. Now, then in step two, it is then slowly warmed. It is then warmed in a very slow way. It is then slowly warmed. So what happens at this point? The gases that exist in that air, I said it has nitrogen, oxygen, and other gases. The gases, they have different boiling points. So as the liquid air is slowly warmed, these substances, they start to turn back into gases once they reach their boiling point. Okay? So I'm gonna write it here. Different gases having different boiling point will start turning back to gas. Now, nitrogen, now the majority of air is composed of nitrogen and oxygen. Now, other mixture of gases is really less than 5%. Nitrogen is almost 78%, and this one 21%, and you just have the rest are other gases. So here, when the gases, they start turning back, when the other substances start turning back to gases, we need to look at nitrogen. Nitrogen has a lower boiling point than oxygen. So it will turn to gas before oxygen. So once nitrogen turned back to gas, anything remaining is oxygen. Okay? So it will remain. So the remaining will be only oxygen in liquid form if we stopped warming it. And then oxygen can be collected. So to like make it simple in few words, I'm just gonna write an answer to this question over here. Oxygen is extracted from air by fractional distillation of liquid air where air is liquefied and then warmed so that the gases in it, the gases with lower boiling point, vaporize first, leaving oxygen to be collected. I hope that the explanation on how to extract oxygen from air is clear. Now moving on, let's talk about halogens. List the properties of halogens. Halogens are non-metals. Let's locate them in the periodic table belonging to group 17. Belong to group 17. They are non-metals and they are in group 17. They can exist as diatomic molecules, like F2, Cl2, Br2, and I2. Now, they are really known to be electronegative. They are electronegative means loving of electrons, and that's because they are non-metals. And F is the most electronegative element of the periodic table. They bond with metals, and when they bond with metals, they form ionic compounds. So they bond with metals by gaining electrons, and they have ionic bonds if they bonded with metals, and a -1 charge. Now they can bond with other non-metals by sharing electrons, and like this they form covalent bonds. Most of them, their configuration, since they belong to group 17, their electron configuration ends like this. So F, it ends 2s2, 2p5. Cl ends 3s2, 3p5. Br, 4s2, 4p5. And iodine, 5s2, 5p5. So their electron configuration ends like this, and therefore they have 7 valence electrons. Any properties you have about, about halogen, just mention it. And that's it. Now moving on to topic 5.4, which discuss the metals. List and explain the general properties of metals. Think about a metal and start listing the properties of metals. Metals, let's start by the bonding. Let's start by like the general properties. They are good conductors of heat and electricity. Just think about any metal, put it in your head, and start listing the properties. Metals are malleable. Metals are ductile. Metals are solid at room temperature, except mercury. Metals are shiny. Metals are silver to gray color, depending on their degree of lustrous. So silver to gray. So some of them are very shiny, some of them are not. So we say lustrous metals can bend. Yeah, I mentioned that. Malleability. So basically, these are the properties of metals. Diamond and copper, they are the only metals that are not silver to gray. All metals are solid except mercury. Iron and nickel are the only metals that can be magnetized. So these are kind of things that you can remember about metals. Now describe the structure of metals. If I look at metals, I see metals next to each other, metallic atoms next to each other, and these metals, they lose their electrons and they become positive. Now, since this electron has nowhere else to go, these electrons, they become floating around. This creates a crystal lattice structure immersed in a sea of mobile, delocalized, moving electrons. So the structure of metals are composed of metallic or metal of cations, you can say, of cations arranged in a crystal lattice structure and surrounded by a sea of mobile, or you can say delocalized electrons. Now they have metallic bonds, so the bonding in metals is called metallic bonds. They form metallic bonds if they bond with other metals, and they are, yeah, that's it. This is the structure. Which of the following metals is commonly found in its elemental form in nature? Now, I'm just gonna give you this hint. In the periodic table that you have, and memorize it. In the periodic table, you have the S block element, you have the transition metals in the middle, and on the side, you have P block elements. Now, if you look in the transition metals, you have 6 elements. You have cobalt, they are right next to each other. You have nickel, you have copper. Under the cobalt, you have it's rhodium or H, palladium, PD, and you have silver. That's it. These are the elements that are found in nature in their elemental form. So remember them. They are in the periodic table. They are next to each other, right next to each other. We call them the noble metals. These are called the noble metals because in nature I can find them alone, uncombined. So, and by the way, we have with them also platinum. We have the platinum. Let me just check the periodic table just to make sure. Platinum is down in here under palladium, but this one is with them. Platinum is with them. So you have gold, you have platinum, silver, palladium, copper, nickel. These are so well known. Describe substitutional alloys. Now, alloys in general is metallic material that contain more than one element, or I can say alloy is a solution of solid solution, of course, of metals or metal and non-metal, because I can mix mix metals or non-metals together. So now let's just so here, if I have an alloy, I have 2 types of alloy. I have the interstitial alloy and I have the substitutional alloy. First of all, I'm gonna draw a pure metal. So here's a pure metal. So let's say all of these elements are copper. Now this is still a pure metal. Now how this becomes an alloy? We need to mix the copper with another metal. So let's say we are mixing it with zinc. Now since copper and zinc have almost the same size, the zinc is gonna come and take the place of copper. So I'm just gonna take randomly 3 coppers and I'm gonna now put instead zinc. Now the size is not gonna change because zinc has almost the same size of copper. So now I have an alloy, and this alloy specifically is called substitutional alloy because it is formed, so it is formed between atoms of comparable radius or size, if you want to say that. Okay, so one atom, like in here the zinc, substitutes the other, substitutes for the other in the lattice. Okay, a good example of substitutional alloy is the example that I just gave, which is brass. It is a mixture of copper and zinc. Okay, now one important thing about substitutional alloys, the malleability and the ductility, it becomes less, the properties become less, and the density, it does not change a lot. It's just it's between the density of copper and of zinc. Now let's describe now the interstitial alloy. Now in the interstitial alloy, I'm gonna take another example. Let's say I have iron. Let me just draw it nicely. I have iron, metals together. So now this is a pure metal. Okay, iron. Now to make it an alloy, we're gonna mix it with carbon. So iron is larger than carbon in size. So carbon cannot come and take the place of iron. So what carbon is going to do, it's gonna fill the holes between the iron atoms. And like this, now I have an interstitial alloy, a mixture of iron and of carbon. Okay, so let me just write that. So the interstitial alloy contain atoms of one kind that fit into the holes or sides of the structure. So usually the mix is between large atoms and small atoms that are small enough that cannot substitute. Okay, so what are these kind of small atoms that can fit into a structure of metal? Sometimes it's hydrogen, boron, nitrogen, and carbon. So they can fit in the closest packed structure. And interstitial alloy, definitely, they are harder because there are atoms filling those holes, and they are less malleable, and they are denser because now the volume is more packed. The space in the alloy is more occupied. So it is harder. The interstitial alloy becomes harder. It becomes denser, less malleable, because those small atoms are filling the spaces between them. Moving on. Complete the table below. Now we have metals, and we need to learn about their properties and their common uses. The best thing is to memorize the information in this table. Now, let's look at the things that we really know. So, zinc is well known to be used as a galvanizing of steel. Copper is used in electrical wires, plumbing as well. So all the electricity and the wires are made up of copper. Cobalt is well known to be used in batteries. Chromium is very shiny, and it's mixed with the iron, and it's mixed to make it to make steel, and it's like shiny. Remember, the stainless steel is very shiny because it contains chromium. It is used in electroplating and pigments. Titanium is a very light metal, but it's hard at the same time. So common uses, it's used for parts of aircraft engines. Now, cobalt, I said, in batteries. Iron is used in buildings, in constructions. So that's a very common use of iron. And nickel is used in coins and alloys. Now, let's look at the properties. Zinc let me start in order and try to memorize these properties. It has a low density and it's corrosion resistant. It's hard. For the chromium, it's hard, brittle. Chromium is the only metal that is not malleable. It breaks easily, and it's a tarnish resistant. Cobalt, again, is hard. It's magnetic. It has, like nickel and iron, it has magnetic properties. It's a corrosion resistance. So as you can see, most of them are corrosion resistant. Corrosion resistant at high temperature. Now, iron is strong. It has magnetic properties. Nickel, again, it's ductile. We make wires from nickel, and it's corrosion resistant. Copper, it's a very good conductor, the best. It's a good electrical conductor, and it's well used in wires, and it's malleable. Zinc, we say lustrous zinc, and it forms oxide layers. Moving on to subtopic 5.5, and the last one, identify the orbitals that transition metals use in the process of filling electrons. Transition metals are found in the middle of the periodic table, and we call it in the D block side of the periodic table. It means here's the group 1 and 2 S elements. You have here the transition metals in the middle, and you have here the P block elements. So here are the transition metals. So all their electrons, they fill the S orbital and the D orbital. So for example, I'm just going to show it to you on the periodic table. if I have, let's say, if I'm writing the configuration of saying vanadium, okay, so vanadium has 2 electrons filled, 1 2 3 4, so has 2 electrons, so 4s2, and then it has 1 2 and 3 electrons, but those 3 electrons we say filled in 3D. So always the S, it's like S, and always the line of D, you take the period and you say -1. Another example, let's say I am writing the configuration of technetium, which is Tc. Tc has 2 electrons in the 5s, so it has 5s2, and then it has in the 4d 1 2 3 4 and 5 4d 5. So all the transition metals, now some of them they might have 1 electron in the s orbital, and that's like an exception because probably in this form they are more stable. So all of them they have either 1 or 2 electrons in their s orbital, and electrons, and can have up to 10 electrons in their d orbital. And because they have these electrons, sometimes they lose from s electrons to form oxidation states, sometimes they lose from d orbitals to form oxidation states, or both. And they have various, more than one oxidation state and more than one color, because they can make more than one oxidation state. Now, properties of transition metals. So again, they might have they have 1 or more electron in their s orbital, and up to 10 electrons in their d orbital. So that's one property. When they are oxidized, they lose the electrons in their s, and then they lose the electrons in the d. So when they are oxidized, they first lose their outer electron that are in s orbital before they lose electrons from their last filled d orbital. They have definitely metallic properties such as shiny, conductor, malleable, good conductor of electricity, etc. Solid at room temperature. Now, they form their compounds are colored. They are well known to be the colored metals. Their compounds are colored because they can have more than one oxidation state. They exhibit magnetic properties, and basically 3 of them: iron, nickel, and cobalt. These are the ones that have magnetic properties. Now, transition metals are solid at room temperature. It means they have high melting point and high boiling point, of course, except mercury, which is liquid at room temperature. They are very hard. Some of them they're not. Some of them are more malleable than others. For example, chromium is brittle. So you need to remember these properties. Good conductors, malleable. For example, lead is very soft, whereas chromium is very brittle. So their malleability can vary, okay? Like this. Now describe the oxidation states of transition metals. They can have more than one oxidation state. The complex ion in CrCO6I3. When it comes to coordinate compounds and complex ions, when you look at the compound, anything that is in the brackets is the complex ion. Now it doesn't look like an ion because the charge is not showing. And whatever is outside the brackets, I call it the counter ion. Now whatever that comes after the metal, this is the metal. So whatever comes after the metal is gonna be the ligand. Now let's just explain it to know the complex ion and the charge in it. I have here CrCO 6 times. Now the charge of this ion should be opposite to the charge of the counter ion. Now I have here 3I. Now I belongs to group 17, so the charge of this ion is -1. Now 3 times -1, that's a total of -3 charge. Therefore, the complex ion will have the opposite charge to -3, and that is 3 plus. What is the oxidation state of lead in lead oxide? Now let's break it. Oxygen oxidation state is always -2 because it belongs to group 16. So I'm gonna assign X to lead. And I have 2 oxygen, each one of them is -2. And lead oxide is a neutral compound because here there is no charge. It's not written next to it -1 or plus something. It's just neutral. So you're gonna say this is equal to 0. Solving for this, you will get X to be +4. So the oxidation state of lead in this compound is +4. What is the oxidation state of chromium NCrCl3? Now again, I'm gonna assign X to Cr and I have a 3Cl. Now every Cl has an oxidation state of -1 because it belongs to group 17. So I have 3 multiplied by -1, and again this whole compound is neutral. Therefore, solving for X, we'll get X to be +3. So the answer is +3. Now the last thing in this focus question is the difference to differentiate between complex ion, ligands, and coordination compounds. Now, the example that I just showed you is a coordination compound. I'm gonna give, let's say, another example. Let's say I have Fe, Cn, 6. Now, this one is gonna have a resulting of 3 minus charge, and I'm gonna use with it a counter ion. I'm gonna put K3. So let me just explain it. K3 is the counter ion. This is the metal, and this one here is the ligand. Now this whole thing is called a complex ion, and the charge of this complex ion is the opposite of the charge of the counter ion. So here the counter ion, I have 3K, and every K has a positive one, so this complex ion charge would be -3. Now let's just explain the difference, or I'll write the definitions of ligand, coordination compound, and complex ion. So a complex ion is usually a metal that is bonded, or you can say combined, to more than one molecule, or an anion. And usually this is called the ligand. Or it could be a molecule that is neutral, or it could be an anion. For example, in this compound here, Fe is bonded to 6Cn. Now Cn is a ligand and it has a charge of -1. Now the charge of the complex ion could be negative, or just like the example over here, it could be positive. This example is CrCO6 3+. So the complex ion can be either positive or be either negative. Just keep in mind that the complex ion is a metal bonded to several ligands. The ligands could be a neutral molecule, or a monoatomic anion, or a polyatomic anion, or a neutral molecule. Now for the ligands, I'm just gonna give you the list of ligands that you should keep in mind. You have the neutral ones, water. You have amine, which is ammonia, which is NH3. You have carbon monoxide, the CO. These are neutral molecules. Now there are other charged ligands, monoatomic anions, like chloride. This one you should memorize it. And polyatomic anions, such as cyanide, such as thiocyanide, sulfur cyanide, and thiocyanate, and the oxalate ion C2O4 2-. So again, these are ligands that are a neutral molecule. This is a ligand that it is a monoatomic anion, and these are other type of ligands that are polyatomic anions. Now the complex ion. The complex ion is formed when an ion, and usually a metal, combines with I need to explain here the coordinate compound. I already did the complex ion. So the coordinate compound is the whole compound itself. Like in this example, the coordinate compound is K3FeCN6. Or another example, the one that was given here, it is CrCO3. These are two examples of coordinate compound. And the coordinate compound is a combination of a complex ion I am highlighting in blue the complex ion attached to a counter ion. So it's complex ion with counter ions bonded to it. All of them, the counter ion and the complex ion, make a neutral compound. To make a neutral compound. Now, the number of ligands added to the complex ion are called coordination numbers. Coordination. And a metal can bond up to 2, from 2 up to 12 ligands. Now, the last question in the focused question, underline the ligand. Again, the ligand should be a neutral molecule. Now, I'm going to mention something about this, or a monoatomic anion. Anion, I mean by this a negative ion, or a polyatomic anion, negative. Now, why it should be like this? The neutral molecule should have lone pairs on it. Like, for example, NH3 and H2O example, there are lone pairs over here. So that's why it's a ligand. It acts as a Lewis base or an electron donor. Now, it could be a monoatomic ion, and the monoatomic ion, because it's negative, it means it has electrons to donate. Or a polyatomic ion, that's the same thing. It has free electrons or lone pairs to donate. So when I look at this compound or at these options, that cannot be a ligand, and this one cannot be a ligand because they have a positive charge, and this can be a ligand because it is negative. And that's it for the focus questions of 12 ASP. I wish you all the best in your end of year exam.